So our next topic, which is 7.4 in the book, is leverage. So the key ideas here are looking at the classes of levers. The third class lever is a speed multiplier, and factors affecting leverage and flattening the arc. So if we have our levers here, we're looking at the result of the actions or the movements in the body result from the actions of body levers. So the levers are like simple machines, and they're generally allowing load to be moved. So we have a combination of bones, which are what give us leverage. So the longer the bone, the longer the leverage. The joint is the fulcrum or the axis point. We have our force, which is our contracting muscle, and we could also call that effort. And we have our resistance, which is what we're pushing against. So we're looking at the class. So we're looking at a first class lever where the axis point or the fulcrum is located between the effort and the resistance. So let's picture a rower in a boat that's got a paddle or an oar that goes out into the water. So we have our pivot point here, or our fulcrum. We have our effort here, and we have our resistance, which is the water. So that's a first class lever. So the second class lever is where we have our pivot point or our fulcrum. We'll get these terms a bit mixed up, but we're looking at something that's our axis point or a fulcrum or a pivot point. Then we have our load or our resistance, call it resistance here, and we have our effort. So if we had a wheelbarrow with a wheel there and somebody wheeling it here, we have our load or our resistance here, we have our pivot point here or our fulcrum, and we have our effort here. So that's a second class lever. So they're very rare, our second class levers. Our first class levers are alright if they've got an external pivot point, and generally we have our third class levers with our internal fulcrum or axis point, which allows us to generate effort through our muscles, and then we have our resistance against that. So if we had holding a ball with our internal pivot points, which allows our effort over the muscle. So effort, fulcrum, and resistance. All right. They can be difficult to figure out. However, what we're looking for is to identify that third class levers are probably our most common. So if we look here, we have our three types of levers. So our first type, our second class, or our third class, and we're looking at what matches each. So the first class lever, or A, is we're looking at the axis is between the force and the resistance. So that is our third definition, where we have R, P, E. So we're looking at, our rower. Our second class is where we have the pivot point, the resistance, and the effort. So we're looking at our first definition, and our third, which is our second. So we can see here, third class matches up to here, first down to here, and our second up here. Those are the correct definitions. So we can see here the first class lever within the body, or if we have our first or second. So generally we're working with our arms. Here we have, if we're pushing up and against, but we want to probably just remind it and remember that this here, the third class levers in most sports generally come from within that body. So if we have levers in sport, Our third class levers are most common type of lever used in our sport. This is because the levers used in sport are musculoskeletal, so this often provides the effort force, and the relevant joint is often the axis. So if we have our pivot points in our shoulder, our effort is generated through the arm, and then the resistance is the bat and the ball there. So when using striking implements, the longer the resistance arm, the greater the speed of the lever. So the longer the resistance arm, the greater the speed of the lever. So if we can increase that lever length, we can then generate more force through the ball. So advantage will be gained because increase in the range of motion. So we might have less control, but we can generate less velocity. So we can see here as speed multipliers. Our axis point, our resistance arm, and then our resistance here. So let's call it a fulcrum, effort, and load. So it's our third class lever, and we have that bigger range of motion. So if we're hitting the ball from here, we will generate less speed than if we're hitting the ball from there. So we can link levers. Many of the principles we've discussed in the book can be connected to levers. A good example is this: if the longer the lever length, so the club plus the arms rotating, the longer the movement arm, greater torque. So we can see here, that's our length of lever. If we shortened it, so the club head was here, we'd have less range of motion, wouldn't we? Therefore generating less force. So increased force applied to the ball, and we'll go through Newton's laws later. We have greater force applied with arms, greater angular velocity of arms, and we have a law of conservation of momentum. So the greater momentum before the collision equals greater momentum after the collision. So that impact and that impact will mean that we'll have that longer period where the ball's in contact with the implement. So flattening the arc, so maximising accuracy versus maximising velocity and momentum. When hitting or throwing the object such as the ball, maximising momentum and speed must always be balanced by the need for accuracy. So the rotational movements of the body may also make accuracy difficult to achieve. So both height accuracy and sideways accuracy usually have to be achieved to achieve maximum target accuracy. So you don't want to throw to go wide or too long. So accuracy in a throw or hit can be achieved if release or impact is made at any point in a straight or direct line to the target. If the hand in the throwing action can be made to move in a straight line towards the target, then it does not matter where the ball is released on that line, the ball will fly to the target at the correct height. So here you can see if the bat, rub, club, racket or throwing arm is made to travel in a flat horizontal or vertical pathway just before the impact or release, the likelihood of the receiving accuracy. The technique is known as flattening the arc. The bat, club or racket or throwing arm can contact the ball at many points on the flattened section of the arc and still achieve accuracy. So we can see here that we're not flattening the arc there. So if we hit the ball here, it'll go out there. If we hit the ball here, it'll go there. If we hit the ball there, it'll go there. Where here, they've flattened the arc here. So if they hit the ball there, there, or there, it will all go in the same direction. So we're looking at kicking this ball. What we want to look at when we're kicking that ball is analyse how the leg is effectively used as a lever in kicking that ball. So particularly explain why initially bends his leg prior to kicking the ball, but then on contact the leg is straightened. Alright, so let's have a look at this again. So we can see here, we go back a bit, the external axis points here and here, a bend to create that longer lever so we can generate swing from there, and as we kick we have that long lever from that, the long lever from the hip. Also, if we're looking at summation of forces, by stepping out, we're generating swing and a contraction in the hamstring, and then we push forward, we relax the hamstring, and then contract the quadricep. So if we think where the internal axis points are, so in there, in the knee, that is generating the effort against the load. So it's a third class lever. And then we'll look at answering the rest of the question. So we can get rid of that. So in simple terms, the leg is a third class lever. The hip acts as a pivot point, like we said. The effort is primarily applied by the muscles in the upper leg, and the resistance is the ball. So that makes it a third class lever. So earlier in the kicking action, the leg bends at the knee. By doing this, we reduce the moment of inertia of the leg, therefore making it easier to accelerate the leg, get it moving. Remember, we reduce the moment of inertia, we increase the angular velocity. So once the leg is moving, we can straighten the knee to lengthen the lever. So to overcome problems of a long lever and its high moment of inertia, many of the movements and techniques used by human body use a combination of short and long levers. So we had the two short levers to make the long lever to reduce the moment of inertia. So in diagram A, the soccer player below, the kicking leg is folded, making the lever shorter and hence giving greater initial acceleration. Because the distance from the point of rotation to the actual moving point, the knee is shorter. In diagram B of the player, the leg straightens to create a longer lever moving faster than any other point to which the lever in turn creates optimal kicking force or power. So remember the case of the tennis racket where the end of the point of the lever travels faster than any other point of the lever, creating that greater force production. So what we're doing here is now we're going to do the questions. And reading from page 275 through to 282. And then we'll be able to move into our Newton's law. So that's what we need to do for homework, page question 275 to 282.